Okay, so we have been going through derivations related to molecular basis for viscosity. The reason we want to do that is that viscosity is a parameter, is something that has been observed in a laboratory setting and really just assigned. Like, let's throw in this coefficient of proportionality into after observing how things work, and then you just basically measure it afterwards using the same Newton law all over again. And there is a real value in figuring out, hey, can we actually scale up from the molecular scale to our laboratory scale and see whether we actually theoretically get something similar to that coefficient of viscosity. So basically what we're looking for is to fit things into our little Newton's law setting where I have tau yx is equal to, and I'm then actually looking to derive what is it equal to in terms of the derivative of the velocity. So we had tau yx is equal to minus mu dvx dy, right? So basically, if I can figure out some sort of relationship between tau yx and dvx dy, I can see whether that holds. I can basically compare to that law. So I have law that I assume based on the observations, and then I have tried to bring the theory to the same level and compare the two, and in that I can try to see which one holds and under which conditions. So we did that for velocity of gases. Gases are easy in the sense that we have kinetic theory where we simplify things down to a very low pressure, low density situation. I have gases that are like molecules, simple molecules that are bouncing around. I imagine them as like tennis balls, and not only tennis balls, but very special tennis balls that don't lose any energy when they collide. And the only thing that I have is perfectly elastic collisions. So in a situation like that, I can have a lot of statistical mechanics formulas that basically relate the properties of those molecules, or statistically properties of sort of ensembles of these molecules, okay, that are bouncing around, and things like that we measure in a room like temperature. Okay. So I keep actually moving scales back and forth. You can actually get dizzy from zooming into the molecular scale, then zooming out at a certain level, and going back and forth in between those. So if you just, there's one thing that I'd like you to remember. So if you remember the question or whatever you remember from the derivation, okay, and then something I need to swap this place. There we go. All right, so quick quiz based on the kinetic theory of gases at low density. What is gas viscosity proportional to? Square root of T. All right, so you remember something. Cool. Now let's go back to the liquids. So in liquids, whoa, we had a derivation, and I'm kind of looking at my PDF for now, and then I'm going to start writing again so I don't need to redraw. So basically what we did again with liquids, okay, we also kind of placed them into a situation of the Newton's law. So I have my layers of fluid, right, where I have molecules. And what we know about liquids is that then we put them in a situation like that, you kind of often have these sort of vacant spots, or that's how they're thought of theoretically, that appear in these molecular cages, except that they're not cages, they're kind of loose, cages in a very loose sense. And then when a spot appears, okay, this molecule, and I'm monitoring this molecule 1 in whatever I call here layer B, okay, I'm trying to figure out, is it going to jump in here? And it is if it's energetically favorable to do so. So I have a distance A to jump. My biggest problem is not the entire distance, but really at this half of this distance, there's this energetical bottleneck, because I have to squeeze between two molecules, and we know that molecules, when they get close to each other, there is a very strong repulsive force. So in order to overcome that, I have to have the highest energy I need to have on this journey is right here. Once I overcome this bottleneck here, I'm going to just slide into the lower energy spot here. So basically the way we represent that is like something like this. So if fluid is not stressed at all, this is sort of my energy levels that this molecule 1 has to have. So here it's the energetically favorable. I'm always looking to minimize energy, right? So this is the spot that it was comfortably sitting in before. But now the vacant spot arrives, so grass is always greener somewhere else. I want to jump, okay? So basically, if I have this much energy, and we call this, we look at the molar free energy of activation. You look at the value that you have per mole of molecules. So then for one molecule, I got to divide it by the Avogadro's number. This number here is given. Do I know this number? No, not really. This is something, well, you fit it from the formulas. You measure it. Basically, it's a fitting parameter that you can measure. So there are some tabulated values for this. So in any event, there's this jump. So basically, I'm gonna, if I have this much energy, I'm gonna jump 2. Now, if I'm in a stressed fluid, that means in a stressed fluid, one possible situation is our Newton's law situation, where I have a plate moving at velocity Vx underneath. So basically, then I have some shear force acting on the little box of fluid that we imagine. Okay? So that shear force acts on all of them, but that's going to make it more likely for a molecule to have this energy, because I'm getting some energy from below. So basically, this force is doing work, a little box of fluid, so there's some extra energy that is put into that box. And that energy makes it more likely to jump downstream along with the flow, and a little less likely to jump upstream. Okay? So we quantified that, and basically this needing less energy basically to jump downstream is basically for this molecule from this position. I now need, only so this is now in green, so basically I now need only this much of energy. Let me show on the screen so you have it on the movie. So basically, this is now my energy of activation if there is a shear force of fluid acting from the outside. If I was going upstream, basically I would have to, you can imagine that you were actually jumping from here to here. So you would need to overcome this entire thing here to actually jump upstream. That's how schematically we interpret this energy. Yes?
And if the molecule is moving downstream, and after the jump, after the peak, will the energy go back to its original magnitude, or will it?
So basically, it goes to this, no. Right? Or this.
I'm talking about the downstream. So if after the jump, will it go like?
It goes to the minimum. So once it's actually in this vacant spot back inside, this highest peak that he has to jump through is in between the two other molecules. But once it's actually in this vacant spot, that vacant spot is actually a minimum, a local minimum of energy as well.
And its local minimum is higher than the energy at rest, right?
Right.
Okay, so it goes back to the same magnitude.
Right. So, yeah, and then you keep kind of doing that all over the fluid, right? Okay, cool. So now that we, yes?
Just curious, does adding temperature also decrease the activation for downstream jumps?
Yeah, I have more energy when I have, so adding temperature is adding energy to the system. That said, we are looking at isotropic, or rather temperature is constant in most. Until we get to the heat transport, we're not messing with temperature. How's that?
Okay.
So we're assuming that my temperature is constant. But yes, that would be another way to move things around. So what we're gonna, so what we actually related here is there's this frequency of jumps, that's number of jumps per second on average. Again, I have to look at things statistically in this world. because it's molecules bouncing in all directions. So that's related to the temperature. There's T here, there's exponential here, and there's this energy of activation playing the role here. And basically, when I have outside force doing work, then basically jumping downstream becomes a little more likely, okay? Because this number is a little less negative, and therefore this number will be larger, okay? And if I'm jumping upstream, then it's less likely because this number is a little more, in absolute value, bigger, which will overall decrease the value. All right. So we labeled our frequencies as plus and minus, depending whether I'm going downward or backward. So when I'm looking at the velocity difference between this layer and this layer, I call them A and B, basically the velocity difference that is there, I'm blaming it on the influence of that force from the outside, so it's the influence of the shear force, and I can quantify that through this extra molecular jumps that are happening because of it, right? So I'm adding work or energy to the little box, and that results in difference in the number of jumps between the faster layer and the slower layer, okay? And this is frequency, this is number of jumps per second. I gotta multiply it with the average length of the jump, and average length of the jump is assumed A. Okay. And then when I look at the actual dvx dy, which is the difference between the velocity of layers divided by the distance between the layers, okay, I put that in, I get this expression. I recognize that this is exponential of a number minus exponential of a negative of that number. And that is basically, I can relate it to hyperbolic sine function. And when I do, we get something like this. So there's this A over delta, kappa tilde over H, multiplied by all of this. Okay. Now, second thing that we're going to look into, so when I actually look at the expression in itself, which is this one, okay, and there was a sine H here, that is a nonlinear relationship, okay? In this world here, I have, maybe I should just rewrite it, but essentially I have dvx dy on this side. I have various parameters that depend on the liquid itself, temperature, these are constants. There's this A and delta I can assume as constants as well. This energy of activation is also constant temperature. So I have really temperature and some other gas parameters here. And here I have tau yx kind of buried under hyperbolic sine. So if I was looking for tau yx being equal to some coefficient times dvx dy, well, good luck. This actually is nonlinear relationship. So overall, what we actually derived is that even in this simplified setting, assuming this theory of jumping into vacant spots is a good theory for this situation, I got that I have a nonlinear relationship between tau yx and dvx dy. That's the reality, even for the simplest liquid. Okay. Now, assuming this number is small, my sine h x is actually very similar to x itself, because this is my Maclaurin series around 0 for hyperbolic sine. So if I do ignore higher order terms, then this is similar, and then I can basically just, instead of sine h of this, I can just write that number. So when I do, this is what I get. Okay. So I have minus dvx divided by dy is approximately A over delta. This entire business here, this is a function of temperature and some constants, times 2 A tau yx, the volume per mole, and divided by 2 delta RT. Remember that these tilde we reserve for molar quantities. So if I evaluate things per mole. Okay. So I have tau yx as minus delta over a square. I'm actually going to be lazy. I'm not going to write. I'm just going to use this. After I set everything up, I'm like, I'm not going to write. I spent 45 minutes fixing up my technology, and now I don't want to use it. Okay, R over. So again, this is constant, constant, constant. This is molar volume. Now, indeed, when I compare to Newton's law, and these laws are really the most helpful when you actually just compare to them and evaluate what an effective viscosity would be in this world. So this indeed is something that just depends on the liquid itself and its temperature times dvx dy. So I have no velocity in here whatsoever, right? This is clear of velocity terms. It really just depends on the liquid, however complicated it looks like. In reality, even when we're fitting to this, these two are actually, so delta G 0 and delta over A squared, those are the fitting parameters that you fit the measurements into. So I indeed, in this situation, assuming that this number is small, so I have done, for instance, I have not very large shear stresses. In that case, I indeed confirmed that tau yx is approximately minus mu dvx dy, mu being a property that just depends on the liquid. Okay? And I will remember this form as more like exponential, so there is a constant over temperature that I'm calling B. And there is some constant in front of it that doesn't depend on temperature. So what I want you to remember from here is more like a form of mu is equal to A exponential B of t, B divided by t. This formula in itself, it does have fitting parameters. Even with fitting parameters, it can be up to 30% off. Okay? So it's not ideal. Liquids are difficult to model, period. Okay? But what's useful from this theory, perhaps the most useful, is that this approximate form is still a pretty good guess. So if I'm going to fit parameters too, I'm going to find A and B that fit this formula. So if I'm having a bunch of measurements and you're looking to fitting or regressions, they only work if you know what functional form do you want to fit to, right? And often you have to go through, so when you have a bunch of data that you're trying to fit a functional relationship to, because having functions is really more useful than just tabulated data, because that's what I can put into simulators. A functional relationship is much easier to put in than just tabulated data. So in all those cases, you need a good functional form to, and sometimes we go through guessing, okay, so the best guesses actually come from theory. Okay? So even if this theory is a little off, there's a real value in basically having a good foundation for your guess. Right? So again, this can be, there's also this energy of evaporation that can be measured. So there are some approximate forms that resemble this that have been explored. There's this one, there's that one. So you can basically fit this to various critical properties of the liquid. But again, what I want you to remember is this approximate form as viscosity of a liquid. Okay, where were we in our discussion? Okay, so this is again the conclusion of the form. So yes, in a specific case, we actually, when we derived, we got the nonlinear form right out of it. But when I actually do a little bit of expansion of that hyperbolic sign, we do actually confirm Newton's law from the theoretical standpoint. Okay? And the general form of viscosity is that of having two parameters, A and B, and exponential of the inverse of temperature. Okay? All right. So when one actually compares this to experiments, it's not, so these are the experimental viscosities. There is Eyring viscosities, so it can be off quite a bit. The percent of error can go up to 30%. Okay. Or even more, way more. Okay. So there is still, for liquids, most of the time we go to tabulated data. Okay. But if looking for the theory is valuable in terms of providing this functional form, what to fit data to. Okay. So theoretical predictions differ. Empirical predictions are much better. So although the theory does provide sort of this understanding, we don't have a very accurate theory for liquids. So Chapman-Enskog for nonpolar gases was working way better. Actually, it was in many cases right on the money. So in summary, why this actually doesn't work is that this intermolecular separation is much larger for gases. Something like, if you remember that Rm value from the critical value where I change my forces from being repulsive to attractive, can be about 10. Like, you actually have gases kind of moving relatively freely without being caged with other molecules of the same kind, whereas for liquids, that's much molecules are much closer together, and therefore intermolecular forces are much stronger. So there's no theory that is comparable to kinetic that works rather well. This Eyring, or sometimes called free volume theory, that we actually use to derive liquid viscosity, is typically 20 to 50% off. There's also no equation for state of liquids. For gases, we have pretty good equations of state, like Peng-Robinson is one that is commonly used, and I think it has 2 or 3 parameters, right? Whereas for state of liquids, you have up to 55 adjustable parameters.
Peng-Robinson can model liquids and gases.
It's used for both, yes, but it's not in itself a liquid equation of state. It's used. Oh well, we can use ideal gas law for everything too. We have nothing else, right? But in itself, it's not derived for liquids, right?
Oh, it's empirical.
Yeah, it's really an empirical relationship. So what we know about liquids is mostly empirical. That's the point. And then it can get more complicated. Our liquids are most often, engineering fluids are not only liquids. Okay? I could have suspensions. Any example suspensions that come to mind?
Slurries.
Slurries. Drilling fluid. Right? Produced fluids can also have solids coming out of the reservoir in petroleum engineering. Any of the funny liquids that you've used this morning? Toothpaste, I hope. Yeah? Maybe you use it, maybe you didn't. So, in any event, those are liquids that actually have suspended particles inside. And therefore, because of that, they sometimes behave more like solid and sometimes behave more like liquid, right? So, in all of those cases, having an actual precise theoretical estimate of how this liquid is going to behave is difficult. One thing that we know, coming back to the toothpaste, is that you have to, if you flip it over, it's not going to flow out of the tube, right? You have to squeeze to flow up. So it has what's we called actually a yield stress, right? So you have to have a minimum stress imposed on that liquid for it to actually start to flow. So it's not Newtonian in the sense that it just goes on its own. But it also can actually have very weird behaviors. So has anybody ever played with cornstarch and walking? Have you seen those videos of walking over cornstarch? Yes? How many of you have? Okay, okay. I'll go at the end of the class. Maybe go search and but basically there's. Do I have it linked somewhere? I don't. I'm gonna do that right now. What was it? It was Ellen. I know it was an Ellen show at some point. Cornstarch. I think it was Steve somebody. There we go. I don't know if sound will go through on this machine now, but oh no, it won't. Well, anyway, I'm gonna narrate. Just let me disconnect my. I'm gonna connect it slightly differently. So there's this starch mixture.
So when you put pressure on it, it doesn't behave like that. So here's what I was thinking. I know you like game shows. So here's my new game show. If you could go from here to here, walking across without sinking, you don't die. All right? So kind of a different kind of game show. So,
and how much have you tested this?
not a lot. We get a little vat of it in the back. And so,
No, seriously, during the commercial, he said we have never tried this before. You just told me you've never tried this before.
Well, that's right. In a small scale, I did, but not like this. All right? But in theory, it should be great. All right? So
This is crazy because no one has done this before. So are you spotting her?
okay. So when you go across,
You go fast.
just go fast. Don't stop. Right? And we're gonna catch you at the very end. All right? But go. It's gonna feel weird. Just go across. Ready? Fast. Go.
You can't stop though. All right, so this is ideal for getting kids into science and all that. But what really happens is you have this starch inside the water, and basically on impact, you're going to expel water from starch, and it's going to solidify on impact. Okay? So you will suddenly have, locally, you're going to have a solid. And then when you don't have that impact, it mixes up again, and then you have liquid and you fall through. So basically that temporary, if she's going really fast, she's actually creating a solid surface to step on. But the moment you stand, you just fall through because you're in a liquid, right? So there's this behavior that goes in between liquid and solid. Okay? On solid, I can stand. On liquid, I fall through. I might be, if I was a little lighter than I am right now, surface tension would hold me, but I'm not that light, right? So gravity will do its thing, right? So essentially, once I have mixtures like that, I can suddenly go one way or the other, and having a way to describe that is actually really difficult. So we're going to get to that a little further, and there's later in terms of expressions for rheology of complex liquids. But even regardless of how complex the rheology might be and how it might change with temperature or with solid fraction or shear stress applied to the liquid, okay, it's great to have a formula, but often even when we have a formula for, let's say, shear thickening or shear thinning fluid or bitumen plastic or one of these formulations that have non-constant mu and mu that changes depending on the situation, right? That still can be extremely difficult to model. So even if I had a simulator that had that inside, okay, I might not use it because it takes a long time to simulate using these formulas. So I will nevertheless actually use this expression of effective viscosity. I will keep comparing to Newton's law and say, well, effectively it appears that this fluid has a constant velocity with this value, right? And maybe a moment over, that value will change, and I'm just going to compare again and change it, right? Instead of actually having a very complex formula of viscosity built into the simulator. So we will always really function in this world of effective viscosities. However my complex system is, I can always actually compare it to the simple law, Newton's law, even though I know it's not valid. For this fluid that I just showed you, this cornstarch in water, that is ideal for Explore UT. And I think it was 1 year there. They did it 1 year. They filled up a tub and had fun with it at Explore UT in March. Okay, Explore UT is a big open house when a lot of people, kids and people and everybody descend on UT for a lot of shows. If you're interested in presenting anything, let me know. I'm always there. So in any way, though I never did this, maybe I should do this tub. That's just for having fun. So basically, even when you have a complex fluid that you know is not Newtonian and it doesn't fit this simple description, you nevertheless still look at the effective viscosity, assuming Newton's law is correct. Okay. So here is some formulas for suspensions. So again, I need to, wait a second. Okay. So apparently I gotta, I'm trying to, but like what I see here is not what I had that problem and I did something. Oh, I'm just gonna work with it as is. I should be able to get with the mouse over to that swap displays and click, but no, it just changes the slide. Oh well. So we're often looking for this effective viscosity, assuming that we have essentially a situation from Newton's law. And even though I know that my actual fluid is this sort of heterogeneous mixture, I assume that it's kind of sort of effective fluid with constant properties and it has some effective viscosity. Okay? So suspensions, also emulsions, are in essence non-Newtonian. We also have a lot of emulsions and foams, so those are another cases of heterogeneous situation where my liquid is not smooth and homogeneous. And as long as they're kind of flowable, right, we're gonna go and estimate effective fluid viscosity. So these are some formulas. This is from chapter 1.6. Okay, so these are the formulas. Effective formulas depend on particle shape and suspension type. So I could have dilute or concentrated suspensions. The most common formula is that of Einstein. This is when you really have dilute suspensions and the suspension particles themselves don't interact much. and there's not a lot of them, then if their volume fraction is phi, then your effective formula, effective viscosity divided by the viscosity of the native fluid is 1 plus 2.5 that volume fraction. So if the fraction is not large, let's say that it's 0.05, right? This is actually not going to change the viscosity of the original fluid much. Okay? Then I might have non-spherical, and then there is this shape dependent factor C, which is really a correction that you fit to this, right, from the data that you have. Then there's a concentrated suspension of spheres that has a little more complex formula. And there's now critical volume fraction here that, again, you have to fit to. And these formulas get more and more complex, basically. The more complex particles you have, you need much more than just one parameter, like a fraction, to fit to. Again, I don't want you to memorize this or whatever, but just know that they're there. So when you're actually gonna use this, say, in your research, okay, there is typically no perfect formula that will work for you. You gotta go and explore the literature and see what formulas have been offered so far. Hopefully do some measurements, or your fellow graduate students does some measurements, or you have some measurements from literature that you can grab for the system that you're interested in. And basically compare if you actually want to use a formula in your, say, simulator or for some other purposes to be predictive for some future situations, then you're going to find the formula that fits your situation well. So always be critical and compare multiple formulas. In different situations, you might be inclined to use different formulas. Things always change, so be on the lookout and know that it's not perfect, but nevertheless, we can actually do a lot if we actually have a little bit of predictive capability to just see where things are going. So again, compare multiple sources depending on your situation. Okay. So just for the couple of minutes left, let's actually do an example problem. So estimate, take a piece of paper, estimate effective viscosity of a 19 weight% aqueous suspension of nanoparticles. So there's plenty of nanoparticles around this department in various research groups. And I'm just giving you, this water molecules are here just for kicks, just to give you the idea how they compare to the nanoparticles themselves. So if you have a 5 nanometer nanoparticle, water molecule is 0.3, so it's not that much different, right? So for water, so we have 1.2 gram per centimeter cube, and the overall density of the suspension is 1.1. So from these densities and weight%, I'd like you to figure out what is the volume fraction of the spheres. And then use one of these. Hint, start with the simplest one, go from there. Always start from the simplest one in your research and go from there. Improve if you need to, if not, let it be. So the key thing is somehow to relate volume fraction of spheres to the densities that I have provided, because that's the information I have provided. Is actually size of these spheres relevant here? It doesn't count, right? So none of these formulas, so that's something to actually observe. None of these formulas say anything about what is the particle size in this whole problem. Though quite likely size, actually there's some critical size up until which one formula is good and then it doesn't become valid and so forth. Partly because so gravity starts working on different sides of the spheres differently, and that can kind of change things. So that's, again, that's a simplification, right? We know that in reality size should matter in some shape or form, certainly on stability of suspension and whether you get gravity settling or not, right? But it doesn't play in these formulas. So that's something to think about. It's a simplification. So it's there. This was just there as a piece of information that you have. And often in problems you will have more information that you know what to do with. Okay? so in any event, so what is the volume fraction? Did anybody?
Yeah, it's 17%. No?
Somewhere there. I don't have it written now, but it was 10 or 11 if I remember correctly. Okay? And then once I put it in this, for instance, this first Einstein's formula, right? Volumetric fraction, so by weight percent, this is 19%. If these are, it doesn't say which nanoparticles, I just see that there's not that many of them and they're not changing density much, so volumetric fraction is probably not large either, right? So, but if I imagine silica nanoparticles are the most commonly used ones, right? Their density is about 2.7 times more than that of water. So then this weight percent will, if I try to translate it to volumetric percent, it's going to be about 2.7 times less than this number, right? So it's not a large fraction. So I'm going to justify that this formula should be okay, right? So if I use the simplest one, okay, then this is now, I don't have any other information that would tell me otherwise. So I'm just going to go with it. So if you put 10% here, 0.1, this is 0.25. So this is effective viscosity is only 1.25 times that of the original liquid. Okay? So that's how the process works. Cool. Don't have much time left. I'm just gonna introduce what are we doing next. So our next topic, so now that we went over molecular basis for viscosity and we have some understanding how good or bad this idea of viscosity parameter is, now we're going to actually move on to another part of the problem, and that is multi-dimensional world that we live in. So far we just said tau yx is equal to minus mu. Let me, I'm going to let writing be for today. Tau yx is minus mu dvx dy, and this was the simple situation where only vx was non-zero velocity. So my system had velocity only in one direction, nicely aligned with my coordinate system, right? Or rather, I moved the coordinate system to align with that velocity. However, in reality, we know that we might have fluid flowing over obstacles and in all possible directions. So we can't limit ourselves to the world where I only have one non-zero velocity Vx. So I might have not just Vx, but Vy and Vz. And as I move around, I could actually have gradients of that velocity in all directions, 3 directions. So I have 3 velocities that describe my liquid at every point. Vx, Vy, Vz, and I have 3 possible directions in which they could change and have gradients. So if you remember your calculus, this time multivariate calculus, so is it calculus 3 or whatever number it might be in your undergraduate program? Then you described your gradients or the way velocity changes with a matrix, right? What was the name of that matrix? If I have vector field Vx, Vy, Vz, and I have all the possible gradients in 3 other directions.
Tensor.
It's a tensor, yes? What was the name of the tensor? The one that has all of the partial derivatives.
Jacobian.
Jacobian. Remember Jacobian? Of function? Well, we will need to relate our viscosity, and it's going to be a tensor. Shear stress is going to be a tensor that relates to all of the possible partial derivatives of velocity. That is the tensor. Fun test? All right. So we're going to do that starting Friday.
Tomorrow?
Oh, Thursday, correct. Tomorrow, 5:30 till 6. Thank you. I have to remember that tomorrow and just show up here and nobody would be here.